The attenuation or transmission loss of optical fibers has proved to be one of the most important factors in bringing about their wide acceptance in telecommunication systems. As channel attenuation largely determined the maximum transmission distance prior to signal restoration, the optical fiber communication become especially attractive when the transmission losses of fiber were reduced below those of the competing metallic conductors like uh, twin wire cable or coaxial cable with less than 5 dB per kilometer of attenuation. Signal attenuation with optical fibers, as with metallic conductors, is usually expressed in logarithmic unit of the decibel. We will see later on what are the advantages of this particular unit decibel. The decibel, which is used for comparing two power levels, may be defined for a particular optical wavelength as a ratio of the input optical power Pi into a fiber to the output received optical power P0 or PO from the fiber, which is defined in this way: 10 log to the base 10 Pi by PO. In optical fiber communications, the attenuation is usually expressed in decibel per unit length. Instead of simple decibel, we used to express in terms of decibel per unit length. So we can write it in this way: the total attenuation is written as alpha dB into L. L is the length of the fiber. That is equal to 10 log to the base 10 Pi by PO. This alpha is actually the signal attenuation per unit length in decibel, which is also referred to as the fiber loss parameter, and L is the fiber length, as I said. Let us try to understand the attenuation in terms of a problem. When a mean optical power launched into an 8 kilometer length fiber is 120 microwatt, the mean optical power at the fiber output is 3 microwatt. We have to determine the overall signal attenuation or loss in decibel through the fiber, assuming there is no connectors or splices. Second one is the signal attenuation per kilometer for the fiber. Third one, the overall signal attenuation for 10 kilometer optical link using the same fiber with splices at 1 kilometer intervals, each giving an attenuation of 1 dB. And last one is the numerical input or output power ratio in the third question. So let us see how we can solve this problem. The signal attenuation, as we have discussed, by definition 10 log to the base 10 Pi by PO. Pi is given as 120 microwatt and PO is 3 microwatt. So 120 microwatt divided by 3 microwatt, and it turns out to be 16 dB. Now this is the total attenuation, right? So from that we can calculate the attenuation per unit length. So alpha into L, that is equal to 16 dB. So alpha, that is the attenuation per unit length, can be written as 16 divided by length of the fiber, which is 8 kilometer. So it is 2.0 dB per kilometer. So third question was, if the fiber length was 10 kilometer, then the corresponding attenuation should be attenuation per unit length into length, that is 20 dB, right? Now point is, the loss due to the splices is 9 dB. How? Because within this 10 kilometer, the splices are done at 1 kilometer interval. So total 9 splices are required, each giving 1 dB loss. So total loss will be 9 dB for splicing. So total signal attenuation will be 20 plus 9, that is 29 dB. And numerical input output power ratio, we can simply take the anti-log, and we can get Pi by PO equal to 794.3. This is the power ratio. Loss mechanism. Here we'll try to understand why the absorption takes place inside a fiber. So we have different type of loss like material absorption, scattering loss, bending loss, radiation loss due to mode coupling, and leaky modes. Now we have said that attenuation is measured in terms of decibel. Now actually the power is also measured in terms of decibel. Okay, we have to familiar with this dBm unit. So it is a special type of unit of power uh, when the reference power is 1 milliwatt. So it is defined in this way. dBm means 10 log to the base 10, the power measured in milliwatt divided by 1 milliwatt. Okay, so 1 milliwatt power, if we convert it into equivalent decibel or decibel milli, and that becomes 0 dBm. 10 milliwatt power becomes 10 dBm. 100 milliwatt power becomes 20 dBm. So in this way, we can convert the power in milliwatt into corresponding dBm value using this relationship.